Some functions are extremely difficult to integrate, like, for example, the function of a circle. So, the function of a circle is defined as x squared plus y squared is equal to radius squared for that circle. Or if you just isolate them in each part, if you isolate for a function of y, you get square root of r squared minus x squared. And this function, actually plus or minus, looks like this. How in the world can you substitute this function in to integrate? Well, it's possible, but very annoying and very difficult to do so. That's why you can integrate with respect to polar coordinates. So, quick recap on polar coordinates. X is equal to r cosine theta, and y is equal to r sine theta. Now, in your general formula for a double integral, you're going to have some function. You're going to have dA. And typically, you turn dA to dx dy or dy dx. Doesn't matter. But for dA, when you're integrating with respect to polar coordinates, you have to add dr d theta. You have to add an r in the front. Or r d theta dr. So, when you turn dA into your actual variables, I don't know what this is called, you have to add an r into it. You have to multiply the entire function by r. So, now this, actually hold up, let's go back. This turns into this. R theta of r dr d theta. So you have to multiply your function by r whenever you're integrating with polar coordinates. So, with that recap done, let's go ahead and start off with some problems. First problem is the integral with this bound here. Y squared and 0 and 1 of our function x squared plus y squared for dx dy. So turn this into a polar coordinate integral. How do you do that? Well, let's go ahead and draw our graph. So 1 minus y squared looks something like this. I think it's this. Yes. 1 minus y squared is the semi-circle, the right half of your circle. And the next y bound is 0. Next x bound, actually. Sorry, this is the x bound. And our y boundaries are 0 and 1. So therefore, our shaded region that we're integrating is this quarter circle here. So how do you represent this in polar coordinates? Well, our radius for a circle is always equal to 1. So r in this case is equal to 1. How about our theta value? Well, our theta value ranges from the x-axis, the positive x-axis, to the positive y-axis. And this is from 0 theta and in radians to pi over 2. And pi over 2 is just the angle at the positive y-axis. Now, keep in mind that our radius isn't only equal to 1 because then we would just be integrating along a circle. Our radius is from 0 to 1. So from radius 0, which is just a singular point, I guess, or something that doesn't exist, I don't know, ask your math teacher that maybe. I'm not a PhD student. But from radius 0 to radius 1, you have the shaded region. And from theta 0 and theta pi over 2, you just go from the positive x-axis to the positive y-axis. And now we have our bounds. So we can actually switch up this integral to make it so that the r bounds are from 0 to 1 and the radian boundaries are from 0 to pi over 2. Now, here's the thing. We have to turn x squared plus y squared into our, hold up, x squared is equal to r cosine theta, and y is equal to r cosine theta. And we have to turn x and y into our polar coordinate function. So how do you do that? All you have to do is substitute in your values for x and y with their polar coordinate values. So you get r cosine theta squared plus r sine theta squared. And dx, dy turns into r dr d theta. Remember that. dA for polar coordinates is equal to r dr d theta. Do not forget the r. And let's actually just make this a little more technical here. Put parentheses around the function. And the thing about this right here is actually not as complicated as it seems, because if you simplify everything within your function, you just get left off with r squared. And I'll just show that real quick down here. So r squared cosine squared theta plus r squared sine squared theta is the expanded form. So if I distribute this power among both of these functions here, this is what we get. We can factor out an r squared, and then all we get is cosine squared plus sine squared. And this is just equal to 1. So this is just r squared times 1, which is just equal to r squared. And that's why we can just say x squared plus y squared is equal to r squared. And with this, if we have r squared times r dr d theta, you get the integral from 0 to 1 and 0 to pi over 2 of r to the power of 3 dr d theta. And if we just keep going, you get the integral. Let's just actually turn this into just with respect to r first. Make this a little simpler. Then you get r to the power 4 over 4 for the integral of r cubed with respect to r from 1 to 0. And then you get 1 over 4. And with this, you can integrate with respect to theta now for 1 over 4 d theta, and all you get is 1 over 4 theta from 0 to pi over 2. If you just plug in 0, nothing happens, so all you have to do is plug in pi over 2, and then you get pi over 8 when you multiply 1 over 4 by pi over 2. So this right here is our integral is our double integral value for this quarter circle of the function x squared plus y squared. So for this next problem, we will use the same function, x squared plus y squared, because it's very easy to use, of dy dx. I actually need to move this integral to get more space. So from -1 to 1 of the square root of 1 minus x squared, -1 minus x squared. So these are our boundaries for this. This is not part of the function. It just stretches out more than it needs to. Let's try to bring them closer to the integral. And if you draw out this bound, you simply get a circle. No. We are not taking a circle that looks like that. I'm going to use the tool. Okay. So our y boundaries is this function up here and this function down here. Actually, I could change the color from 1 to 2. This red outline part is just the function -1 minus x squared, and this blue outline part is our function square root of 1 plus x squared minus x squared. And remember, the top bound of the integral is our top boundary for our region, and the bottom bound for the integral is our bottom boundary for our region when integrating with respect to y. So for this is just our boundary. We can honestly just shade this in, and the x bounds are just from -1 to 1, which just looks like this. But we don't need that because our y boundaries tell us enough. Let's actually undo all that. So for this problem, we have a full circle compared to the last problem, we had a quarter circle. And we were given that the radius is 1. The maximum radius is 1. Actually, you know what? I could... No. No, I'm not going to change up the problem. The maximum radius is 1. So our radius is from 0 to 1 for r. And since this is the full circle, we can actually set theta all the way to 2 pi. So previously, we turned x squared plus y squared is equal to r squared. And this is actually an identity. You can memorize this. X squared plus y squared is always equal to r squared whenever you're transforming into polar coordinates. And our new bounds are, or our new integral looks like this. So the radius is bounded from 0 to 1, and our theta is bounded from 0 to 2 pi. Our function is r squared, because x squared plus y squared is equal to r squared, and we have to multiply by dr d theta. So with this, you get the integral of r to the power of 3 dr from 0 to 1. And then if you solve for this integral, you get r to the power 4 over 4 from 0 to 1 for r. If you plug in 1, you get 1/4. And then, now we integrate with respect to theta. So we get 1/4 d theta. So we get 1/4 times theta from 0 to pi over 2. And all we have to do is multiply 1 over 4 by pi over 2, which I should have wrote here. And 1 over 4 times pi over 2 is simply, 2 pi is pi over 2. There you go. This is our double integral when we integrate the same function, but instead with the entire circle. Now, for this problem, I'm going to give you the function, and I'm going to draw out the region for you and give you the necessary information, and you're going to set up the integral yourself. So our function is just x times y, and our integral, when our bound will be along this semicircle and this semicircle, and the radius for this is 1. The radius for this bigger semicircle is 2. Your shaded region looks like this. So try and do this. Set up the integral and then solve for it. Now, for this integral, it's a little different than the others because the radius doesn't range from 0 to something, 0 to 2. It actually ranges from 1 to 2. So we have to take that into account. And our theta value is from 0, which is the positive x-axis, and the negative x-axis, which is just pi. Now we can set up our integral. 1 to 2 is our radius, and 0 to pi is our theta value that we're integrating. But here's the thing, we need to turn xy into polar coordinates. So x is equal to r cosine theta, and y is equal to r sine theta. So we just have to substitute the polar coordinate transformation for this. And we also need to add r dr d theta because we are using polar coordinates. And later you're going to learn what this value is here, but for now, just trust the process. So for this, we can actually simplify this integral just a little more. Turn this into 1, 2, 0, pi, and this is actually r to the power of 3 cosine theta sine theta. Ran out of space there, hold up. Sine theta of dr d theta. So let's go ahead and start this. We will integrate 1 to 2 with r to the power of 3 of cosine theta sine theta. And what actually happens here is, and we'll integrate this with respect to r, these theta functions for cosine and sine are treated as constants currently. So we can actually move them out of the integral, if that helps. But I'm just going to integrate this without that. So what happens is we get cosine theta sine theta of r to the power of 4 over 4, because that's the integral of r cubed, from 2 to 1. Now all I have to do is just take this somewhere else. We'll plug in 2. So 2 to the power of 4 is 16. 16 over 4 minus 1 over 4, which is just equal to 15 over 4. So 15 over 4 is our integral with respect to r. 15 over 4 multiplied by cosine and sine. So what we can do is write the integral again. And then we get cosine theta sine theta times 15 over 4. What actually happens is we can take out 15 over 4 this time out of the integral, since it's a coefficient, and then integrate this with respect to theta. The integral of cosine times sine is sine to the power of 2 theta over 2. And then our boundaries are from pi to 0. If we plug in pi for sine, you get 0. If you plug in 0 for sine, you also get 0. So 0 times, let's actually multiply. It's kind of useless, but 15 over 4 times 0 is equal to, not theta, is equal to still 0. So our integral for this problem is 0. Now for the last problem, we'll be integrating from 0 to, negative 2 to 2, with our top bound being 4 minus x squared, square rooted, and our bottom bound being 4 minus x squared as well. So this is just a circle with radius 2. And our function is going to be e to the power of x squared plus y squared of dy dx. And all I have to do is draw out our circle with the radius 2 and just shade it in. Let's just shade it in. Now with these functions, we can set up our integral. And this integral turned into polar coordinates is, so let's actually write out our bounds. The boundary for the radius is from 0 to 2, because our radius is 2. And the theta value is just from 0 to 2 pi, because it is the full circle. So if we set up our integral, we get 0, 2, and 0, 2 pi, and x squared plus y squared is equal to r squared. So we have e to the power of r squared. And dy dx turns into r times dr d theta. So this is our integral now. If we integrate from 0 to 2 of e to the power of r squared times r of dr, you can use u sub to find this integral, but I'm not going to spend my time on that. And then the integral of this is 1/2 e to the power of r to the power of 2 from 0 2, 2. If you plug in 2, you get 1/2. You get e to the power of 4 over 2 minus e to the power of 0, which is just 1. So we get 1/2. If you want to simplify this even further, actually, you don't have to. And now all we have to do is integrate this. E to the power of 4 over 2 minus 1/2 with respect to theta from 0 to 2 pi. And if we integrate this with respect to theta, we get e to the power of 4 minus 1. So I just simplified this fraction times theta from 0 to 2 pi. So all we have to do is multiply this entire thing by 2 pi, and then you get 2 pi e to the power of 4 minus 1 over 2. You can actually distribute this 2 pi if you'd like. I don't know, I'll just write this down maybe if you distribute it in your work so you can check it yourself. But this is the final answer. And this is actually simplified. You can actually simplify this. This is pi e to the power of 4 minus pi. If you want to factor this even further, you get this. So if you have any questions, put it down in the comment section.